Thanks everyone. I'm surprised that everyone's still here because this morning when it was raining, I was thinking, oh shit, it's going to be late. So the talk today will be a bit more light-hearted, given that it's going to be the first talk today. Although that's usually my style of giving presentations. I don't like very science and very techy presentation. So you can see that it's going to be a very laid back sort of presentation that going to cover, I guess, the chair had very graciously gave me a very nice introduction, so let's read this one. I do have a conflict of interest, and then just for formality, I have to declare some potential conflict of interest given my startup in Malaysia. So a little bit more background about myself from extending from that introduction earlier is that throughout my career as a genetic researcher, I actually went from being someone that works on very technical stuff into something that's very not technical stuff. There's a few benefits to that, I guess, is because when we are thinking about biobank data infrastructure, it's much easier to convince policymakers, it's much easier to convince the important stakeholders like higher management about what you're trying to do with data when you actually know how to code and know what you're trying to do with those data rather than just hearing that, oh, this is the biggest next biggest thing from UK Biobank, this is the next biggest thing from Illumina. You don't wanna you wanna be rooted in real science and having the real the correct level of reputation to be able to push things forward. So just a little bit of a shameless advertisement about my lab is that we work on basically any human complex traits. So I'm a very big fan of collaborative research, and almost all of my projects that I initiate would have to have a data-driven strategy component. We'll talk about that a bit later. And then in terms of who are we answering our research questions for, is that we are answering it for researchers, policymakers, and early adopters in healthcare, which is basically SMEs and startups, right? In terms of what we kind of do as a lab, we cover both very technical and broad aspects. We probably won't have time to go through both of these, but basically one is more like a meta review where we look at 200, 300 different papers and say, okay, what is the new gold standard that the field have been adopting since this kind of Mendelian randomization or this kind of GWAS study are becoming more prevalent? Is there a very big issue with how people are not understanding certain part of the methodology correctly? And what can we do about that, right? And then the other one is a very nice collaborative work that we managed to work with my genome, is that we basically wrote a very nice position statement for the precision medicine roadmap for Southeast Asia across 7 big ASEAN precision medicine initiative leaders. Our collaborative network in LMIC is quite biased towards Malaysia, given that I'm Malaysian myself, so I shamelessly admit to that. And the learning objective for today, I guess we are just going to cover some and start get thinking about what is a biobank first thing, why a definition of precision medicine is so important in this modern era. And I will also challenge some very conceptual understanding about biobank and how it has evolved over time. And lastly, probably this is going to be the main gist of it, is I'm going to show you what an AI integrated biobank model would look like. Right, so precision medicine, this is probably the most generic slide you can ever get, with precision medicine being development of complex of an initiative or basically a concept where complex diseases are diseases with very complex etiology. There's a combination of environment, social, and as well as genetic. And then recent efforts have been in trying to personalize medicine to some extent. And precision is just another word for personalization in a more statistical manner. Many people argue about different definitions for precision medicine. Just to cover up myself, these are some of the more commonly interchangeably used precision medicine definitions that you will see from all these different organizations as well. But the idea is very simple: tailored treatment based on a person's specific risk profile and specific behavior, right? And then on the other hand, we have to understand as well what's a biobank. So basically, a biobank is just a bunch of participants spit saliva or give some blood. We store their samples or we store their tumor into a biobank, and the biobank will then be used to generate a lot of very useful data. These are a snapshot of all the different biobanks around the world. As you can see, most of them are heavily European-centric, which is also one of the major themes of my research as well, which is trying to address this diversity gap where there's, obviously the amount of Eurocentric finding is not sort of proportional to the right proportion of ethnic representation around the world. And this obviously have very important implication on disease risk prediction. As you can see here, like if you are generating genetic risk score, you are identifying genes that are not as common in Southeast Asian, or you are missing out potential deleterious mutation in a human population that is not ancestrally similar to European, then chances are you won't find it, right? So the misclassification of risk do possess a very huge public health impact, and then there have been work in this space just to acknowledge that this is an existing limitation for most biobanks. So efforts to narrow the diversity gap is obviously there are more bigger and bigger studies around US, around UK, trying to say, okay, diversity is an issue, so let's start putting more Chinese in, putting more Africans in, and blah, blah, blah. And we're also developing a lot of new methods to be able to address the lack of ethnic representation, and how do we create a very nice genetic risk prediction model. There have been a lot of applications in diabetes, in cancer, in cardiovascular, in literally any disease that you can think about, right? And this is basically trying to use statistics to try and fix some disproportionate representation problem. And I'm just way off time. Okay. So on the other hand, if you look at the ASEAN perspective, there are some biobank around the world as well, around ASEAN, that this is probably a bit too small to see, and you can see my genome is somewhere right here, right? So obviously the ASEAN as a region is trying to move into the, the biobank race as well, into kind of encapsulating both discovery science, genomic science, precision medicine, digital health, all in a very big mixed bag. As you can see here, different countries are progressing at a different speed, and obviously we are not that far behind. But let's think about the topic for today. Is that although we know that all of these things are developing, in the spirit and the context of precision medicine, but what has actually changed over time is that if you would have read the literature for precision medicine, or how precision medicine was a major, genomics was a major enabler for precision medicine, this concept of precision medicine being tied on to something that is biological and it's blood-based will have to change, because if you look at some of the more recently published work, and with the advent of AI, we are now moving from tumor genomics into digital biomarker about 5 years ago, and then now we are looking at system-level multimodal precision medicine models. So another way to look at it from a bird's eye view from above, right, is to say, all right, on one hand, there are bits that are about genomic diversity, and then these are all your RNA, CTRs, ctDNA, omics, blah, blah, blah. These are basically the AI automation that's enabled through stronger and stronger GPUs and AI. And then there's also a need for real-world translation as well, because you need to be able to put discovery science into translational value. So the combination of all these three nexus will become the new frontier for precision medicine. Obviously, this is not a very far-fetched concept, because there have been some application across UK, US, Finland, Estonia, and Qatar, which they have already integrated some aspect of AI into their biobank models, right? And this, I feel, at the personal capacity, is a very important revelation because from studying the shift in global trend, you can expect that if you're not obsolete already, about 3 to 5 years time, most analysts are going to be forced to work with agentic AI or work with any of this, be managing this workflow rather than coding or building this workflow by themselves. Because guess what? There's been a lot of speculation that will AI replace your doctors, and then you have all this heated debate or philosophical dogma about whether that's true or not. But we're not going to get to that. But what we're gonna see is that this is going to be a converging trend where AI is going to be needing biobank because it's the biggest source of data, and this is a very nice snapshot about what AI and can complement the mass scale of human biological data and create a lot of very useful insight about it. Like this is, for example, the combination of DNA, RNA, epigenomics, and digital pathology, combined with link outcomes and the ability to what we call dynamically consent for patient, right? So if you imagine if you're running a hospital, you have a biobank, and you have the whole consent system worked out in such a way that, and it's left good. Yeah, we're more than halfway through. I'm proud of myself. Basically, if you think about you're running a hospital biobank, right? Then obviously you have patients, and compared to, let's say, how cohorts or case control studies are run in the past, where people consent for collecting their blood to do experiment X, right? And then when experiment X finishes, you have to hapus scan the blood and all that. Dynamic consent allow for that same biological sample to be retained for a much longer time and for multiple purposes, right? So it's a very important requirement when you think about scalability. Because if you look at UK Biobank, you look at all of us, you look at any biobank that you pick around the world, I bet you at some point they started with 500, they started with 1,000 for the POC, 10,000, they just keep scaling that way. So biobank basically provide this structured access to the consent to be contact 500,000 people, put them on wearables, 500,000 people put them on accelerometer, 500,000 people put them on a DEXA scan for body scan. So this is how a lot of the European biobank became really, really massive, because they have a very, very structured consent model, and every layer of data that you add into it creates more value because it's all linked together, and all of this enables multimodal input and multimodal research. And in fact, most of the more recent biobank have now evolved into a massive longitudinal cohort, right? So these are some of the more clinically relevant application if you want to think about it in the AI space, right? Why does biobank data matters? You can use it for early detection, you can do it for risk stratification. Because most biobank run for 10 years, 15 years, or even 20 years, you can even start building survivorship models that can combine basically things like polygenic risk and then all the real-world hospital data. As long as someone that is part of UK Biobank walks into one of the hospital affiliated with UK Biobank, that record gets updated, right? And then the data just becomes bigger and bigger, a bit like real estate if you think about it, right? So what does the AI party look like around the world? These are some of my key favorite examples. So the most recent application for UK Biobank is actually with My Future Health, as well as with this thing called DeepMind from Google. So Google actually designed their brain morphology scanning protocol based on the same protocol that they use for UK Biobank. So there's going to be a lot of integration with how AI technologies and biobank are going to be scaling together, both in terms of research as well as commercial potential. FinGen, the Estonia biobank is a very, very interesting one because Estonia has the same population size as Sarawak. So in fact, our colleagues back in Sarawak have been exploring, this kind of biobank design as well, where with a population of about 3 million people, they managed to literally sequence everyone that's been born since 1995 or 96, right? So they have basically a record, a digital twin replica of someone since birth. And this data set is just going to get richer and richer as people move into 50 years old, 60 years old, 70 years old. You can think about this as literally someone's life in simulation, right, with AI. So future-proofing biobank projects fall into few key core ideas, right? First is to say, okay, are we then building cohorts that actually fill the ancestral gap? Because what's the whole point of building 20, 50 different European biobank where most of the Europeans are only 5% of the population around the world. So that's inclusive recruitment. They need to be AI ready, and we'll talk about that. How do we build models that are AI ready? And implementation focus is that you need to create a lot of use case along the way, because mostly it's not going to fund a 300 million project on something that's conceptual. You need to be creating use cases along the way to be able to scale biobanks. So this is perhaps a very small cartoon to show you what a biobank input and AI integration in the future or currently would look like. That you're going to have genetics that's coming from the blood, and digital pathology, you're going to have clinical data, and nowadays people are moving into things like wearables, digital omics, they're doing lifestyle data, nutrition. Later there will be a speaker talking about nutrition, so there's a lot of scope in putting lifestyle data, combining it with hospital records, ICD-10, all this big chunk, which wouldn't be humanly possible to analyze in the past, will now be able to be crunched using multimodal AI, because that's what machines are built for. They are built to streamline mathematical optimization that the human mind cannot comprehend. And then you can then create some kind of an output, have a predicted risk, and then if you're a little bit more fancy like me, then you will probably layer another layer of ChatGPT or LLM and say, okay, you write it in plain English or plain Hindi for a Hindi customer. All right, that's what you need to eat. You need to eat vegetable X, Y, Z, to keep healthy. Right, so that's the kind of AI integration and a very nice use case that you can use to convince why building an AI integrated biobank matters. In terms of the more tech-savvy people, infrastructure will then probably look something like this, where you have a data lake layer. The data lake layer is where you have all this genetic data and the clinical data, and then you probably have some level of censoring right here, and then you have an API layer where external applications, whether it's researchers, whether it's companies, whether it's startups, whether it's government agencies, will then be able to API into this whole database and query them accordingly. That's probably a much better visualization, where you have the raw layer. So this is where you lock your consent for governance. And then the harmonized data lake is the layer where everything is harmonized using a common data model. And then this is the serve layer where everything is harmonized, and then you can create a bunch of applications right here. And with AI, this process is just going to get much easier. So this is one example of an API call where you can API into potentially a biobank, a bit like the ChatGPT style, right? You can input it and say, okay, I want to get this specific genotype for this person, and then the output that comes back from the biobank end with the computation will then be that, okay, this is a risk score, and then the interpretation is blah blah blah, and then you put this into your agentic AI whatever and layer another layer further. Or you can even build something like synthetic cohort, which is what a lot of pharma companies are already doing with real-world data like IQVIA, where you can basically build smaller baby data sets and say, okay, I want to query just for South Asian around this age range, everyone with diabetes in the past 5 years. They then return a cutoff of that data set on the fly, right? So in the past, this whole process will probably take 2 weeks or 4 weeks or even 3 months if you are not friends with IQVIA. But right now, this is probably going to take less than a minute, right? With even moderate internet connection. Obviously, this is probably a bit more future-proofing, and giving you one example about a cardio project that we've been working on with the Sarawak General Hospital. Is that you can actually then also combine a lot of all these risk prediction model like genomics, blood-based biomarker with wearable data, right? Because in the past, wearables are not something that's very easy to analyze, because you obviously you can't get someone's ECG data for 72 hours and get a 5 PhD student to look at the peaks. But with AI, you can. So this is one example where we are using a combination of wearable and some of the blood-based biomarker to predict recurrent after cardiac events. So this is another example of how, probably I've shown this already, but yeah, this is just to summarize how we would layer all the APIs together. And this is a very nice paper if you would like to read a bit more about how AI agents are actually changing cancer research and oncology. Obviously, we have discussed some of these key challenges, so obviously what needs to happen from now on is that before you think about building a biobank, you need to first think about harmonizing all your existing cancer-related cohorts. The technical and governance framework is more about consenting, and the policymakers need to be aware about their consenting models. And you need to prospectively design questionnaires and all these things in anticipation that the data set has to be AI ready at some point. So this is probably just a very small snapshot about what we have been working on as a technical research group. We are doing something like federated learning, where we that's good because I only have one slide left. So this is basically an example of how we can do machine learning even when these three data sets are fragmented, and that's through something called federated learning, which we are co-developing with a few partners. This is just another study that we are building the next generation precision oncology for glaucoma with USM. So that should be it, and happy to take any question after everyone's session. Thank you.